Not enough. Hey, Devin. This is that problem you and Mr. Hagen were working on in the math club Wednesday after school. There's a lot of really good advanced algebra review in this problem. I'll be really curious, and I know Mr. Hagen will too, to see if you come up with a solution using the base 3 logarithms that you had on the board. When I shared my solution, I was obviously talking way too fast. So since this problem is rich with review, I figured I'd slow it down a little bit and share the strategy I used in case you might find it interesting. The first step was to use each ordered pair of x and y, substituting in to create a system of 3 equations. Next, I solved for this variable c and substituted it into the second equation. We substitute it right here, so the new equation is that. Then, I'll solve this equation for c and substitute that expression into this equation here. That means we'll have 3 equals this log plus that expression. Well, now we have a new system of equations, and we've reduced our system from one of 3 variables to one of 2 variables. What should we do next? Next, I isolated the log expressions and collected my constants on the left for both equations. Now, why is this helpful? Because we have this rule, this property of logarithms that you learned in advanced algebra 2 years ago, which says that the logarithm of a quotient is equal to the difference of those logarithms, or in other words, going in the other direction, the difference of 2 logarithms is equal to a single logarithm of the quotient of those values. So we're going to use this property going from the right to the left to rewrite the right sides. So we have -1 equals the single logarithm of the quotient of this binomial and this binomial. Same thing, -1 is, and we'll rewrite this difference of logs as a single logarithm of the quotient 11 plus b over 5 plus b. All right, next we're going to use another property of logs, or actually the definition of logs. Remember that if a log base a of b is equal to c, remember that the logarithm is equal to the exponent. So c is the exponent that you'd put on the base a, because this is log base a of b is equal to c. And if the logarithm is the exponent, then c is the exponent on base a that yields the value b. So we're going to do that. We're going to change from log form to exponential form on the right sides of the equations. Remember, the logarithms are equal to the exponents, so these will be exponents on base a. All right, so by the transitive property, these rational expressions have to be equal to each other. They're both equal to the same thing. So when we solve this equation, we will know b. Once we know b, we can substitute it back in, and then we'll know a, and onward. It bears mentioning that b cannot be -3, nor can it be -5. Otherwise, these expressions would be undefined. Anyway, let's keep on solving over here. So b is -2. Therefore, what is a? So a to the -1 power is 3. Therefore, a is a third. And as for c, remember that c was equal to 4 minus the log base a of 5 plus b. We could have really used any of these. This was from the middle one. So if a is 1/3, we'll put that right there. And b is -2, so we'll put that right there. So c is 4 minus the log base 1/3 of 3. So let's evaluate that. Remember, we're trying to figure out what this is equal to. And it's equal to an exponent. So what it's equal to is the exponent on 1/3. That yields 3. And of course we know that 1/3 to the -1 is equal to 3. So that question mark is -1. So c is equal to 4 minus a -1. So c is equal to 5. Well, Devin, I hope this was interesting. Like I said, I think this problem was a very good review of advanced algebra topics, like setting up and solving systems with a substitution method, properties of logarithms, the definition of a logarithm. However, I have no doubt that there's a different way to solve this problem. And if you find a different way, I would love to see it. So please do share if you come up with a different solution.